In this video, we will discuss priority scheduling. In the priority scheduling, a priority number, normally an integer, is associated with each process. The CPU is allocated to the process with the highest priority. Here, the low priority value represents high priority. That means higher priority tasks have numerically lower priority values. For example, the priority value 0 and 1 means a higher priority. If a process has a priority value 1, means this process have very high priority. If a process has a priority value 10 or 15, means that this process has a lower priority. The equal priority processes are scheduled to run on the CPU in first come, first served order. Because there may be multiple processes in the ready queue. Some processes, they have equal priorities. These processes are run on the CPU or are dispatched to run on the CPU in first come, first served order. Who arrives at the ready queue first? Which process will be scheduled to run on the CPU first? The shortest job first scheduling is a special case of priority scheduling. Here, the priority is the inverse of the predicted next CPU burst length. The larger the predicted CPU burst, the lower the priority. The priorities can be defined internally or externally. Internally defined priority use some measurable quantities such as memory requirements, the number of open files, or the ratio of input-output burst and the CPU burst. Normally, if a process requires more resources, requires more memory space, and need more open files, this process may have lower priority. Externally defined priority use criteria outside of operating system, such as the importance of the process, the amount of fund being paid for per computer user use, the department sponsoring the work. For example, a process is very important, and this process may have a higher priority, and the user pay more money for the computer use. The process or program of this user may have the higher priority. The sponsor department, their program or process may have a higher priority. The priority scheduling can be non-preemptive or preemptive. When a new process arrives at the ready queue and the priority of this new process is higher than the currently running process. For the non-preemptive priority scheduling, this new process is inserted into the right place of the ready queue. The current running process continues to run on the CPU until this process terminates or this process is blocked. So the current running process will not be interrupted by this new process. This is a non-preemptive priority scheduling. For the preemptive priority scheduling, the current running process is preempted or is interrupted, and the current running process changes the state from running to ready. The running process changes the state to ready, and this process is inserted in the ready queue. The new process with the higher priority is dispatched to run on the CPU. And now let's take a look at an example of preemptive scheduling. This is a preemptive priority scheduling. Here we have 5 processes, the same data we used in the previous 4 scheduling algorithm, but the only difference is we add the priority value for each process. Now the process A, the priority value is 5. This means the process A has the lowest priority among 5 processes. And the process C, the priority value is 1, means process C has the highest priority among these 5 processes. And then the process B, the priority value is 2. It also has a higher priority. And then this is the arrival time at the ready queue, the length of CPU burst time. And now let's take a look at the execution order of these 5 processes. Now at time 0, process A arrives at the ready queue. Process A priority value is 5, but now A is the only process in the system. A is selected, run on the CPU. A is running. At time 1, A is running. At time 2, A is running. At time 3, A is running. And then at time 4, process B arrives at the ready queue. B is the only process in the ready queue. Process B's priority value is 2. A is the current running process. Its priority value is 4. So 4 is greater than 2. That means process A's priority is lower than process B's priority. For the priority, the lower priority value means a higher priority. So B has a higher priority than A. A will be interrupted. Now the A is added at the end of the queue. A priority is 5. Now B, the new process, is dispatched to run the CPU. So at time 4, A is waiting, B is running. And then at time 5, process C arrives at the ready queue. Now the process C's priority value is 1. So C is added at the front of the queue. And also when we compare the priority value of process B and C, process B, the priority value is 2. And process C, the priority value is 1. Here we get this value from this column. Now the process C, the new process, has a higher priority than the current running process. So process B at time 5, process B is interrupted. Process B is added in the ready queue. And process C, the new process with a higher priority value, with a higher priority or the lower priority value is selected, dispatched to run on the CPU. Process A and B are waiting in the ready queue. Okay. And then after one time unit, process C terminates. Now B is at the front of the queue. B has a lower priority value, or B has a higher priority than A. So B is selected to run on the CPU. B is running and A is waiting. At time 7, okay, B is removed from the ready queue. Now at time 7, A is waiting and B is running. At time 8, A is waiting and B is running. And now at time 9, process D arrives at the ready queue. Process D, the priority value is 3. So now we add process D priority value 3 in front of process A. Because D has a higher priority than A, D is inserted in front of A. Now, also at time 10, process B terminates. Process D already run on the CPU for 4 time units. So process B terminates 4 time unit of the CPU burst time. And now at time 9, process D is selected. Process D is running on the CPU. A is waiting in the ready queue. Process D terminates after 1 time unit. And now A is the only process in the ready queue. A is selected, dispatched to run the CPU. And time 11, A is running. And then at time 12, process E arrives at the ready queue. Process E priority value is 4. A is a current running process. Its priority value is 5. So the current running process has a lower priority than the new process. So process A is inserted in the ready queue. Priority value is 5. And E is selected and dispatched to run the CPU. So A is interrupted by E. Now E is running and A is waiting. Times 13, E running, A waiting, E running, A waiting. Now at time 15, E terminates. A is selected and dispatched to run the CPU. Now after time 15, process A terminates. 4, 5, 6, 7 time units. A runs on the CPU for 7 time units, A terminates. Now let's take a look at the waiting time of these 5 processes. The waiting time of process A is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 time units waiting in the ready queue. And the process B, 1 time unit. And the process C, D, E, the waiting time are 0. The turnaround time equal to the CPU burst time plus the waiting time. This is a 5, 1, 1, 3. The work ratio equals to the CPU burst time divided by turnaround time. 7 divided by 16 equal to 0.44. This is a 4 divided by 5 equal to 0.8. And for the process CDE, the work ratio are 1, 1, 1. Now we can calculate the average waiting time. The average waiting time 9 plus 1 divided by 5. This is 10 divided by 5 equal to 2. The average waiting time for each process is 2 time units. The average work ratio, this is 3, the 0.44 plus 0.8 plus 3 divided by 5. This is equal to 0.85. Now from this example, we can see the process A has a lowest priority. Now the waiting time of process A is longer than other processes. Process C and D, process C has the lowest priority value. C has the highest priority, and its waiting time is 0. And the average waiting time for the preemptive priority scheduling is 2. This performance is very good compared with other scheduling algorithms. And also the work ratio is very high. It's better than other scheduling algorithms. Here is the major problem with the priority scheduling algorithm is lower priority processes may starve, are subject to starvation. Because the arrival of higher priority processes can prevent a lower priority process from executing or from getting the CPU. The lower priority processes may stay in the ready queue forever, never have the opportunity to be scheduled to run on the CPU. To solve this issue, we can use aging. Aging means gradually increase the priority of a process. If this process stayed in the ready queue for a long time, so we will gradually increase the priority of a process until this process is dispatched to run on the CPU. Okay, this video will conclude here.